So the recording is started, and then I'm going to go ahead and export this whole attendee list from Constant Contact and then add them to the webinar meeting. So Jim, I guess, if we want to do introductions real quick, my name's Brett Connell with Trinity Environmental Solutions, and Jim will be putting on the presentation. So Jim, I'll go ahead and hand it off to you while I send out these invites again.
Sure. Well, welcome everybody. We'll be talking about a project doing some submerged aquatic vegetation mapping down in Florida. I'll start the presentation, but Dr. Exum here is going to begin and say a few words. And I'm going to, like I said, I'll get this started. I'll have to move a few things around, make sure it pops up. Get this started, of course, with all these different screens. Go right up to the start. And switch it to that one. Now we're on the overall conclusions. I don't know how we got to the very end. Okay, so the presentation today is going to be on submerged aquatic vegetation mapping using a high-definition stream survey on the Wekiva River, which is sort of northeast of Orlando in Florida. And you can see a little video here, but I'm going to move on. And Jay, would you like to say a few words?
Yeah, thanks, Jim. I appreciate the opportunity. I will say that I am on the board of a nonprofit called the Friends of the Wekiva River, which you can see is one of the entities on the Comprehensive Management Committee of the Wekiva Wild and Scenic River System. So the Wekiva is a federally designated wild and scenic river. So there's this management committee that funds projects related to natural resource protection in the river. And to give you context, because I was going to say, I don't know where everybody's from, but I see that we have people from Alaska. So the context here is that this system is north of Orlando in central Florida. There are about 50 miles of spring runs, rivers, and creeks in this system, and 32 named springs that feed these rivers in what we typically refer as the Wekiva River system. Jim, if you go to the next slide, there we go. So by far the most important submerged aquatic plant is eelgrass, Vallisneria americana, in the Wekiva River system. And it is abundant, like you see here, in patches, but in other spring runs of the St. Johns River Basin, there have been some sort of highly publicized collapses of eelgrass. And because of its importance, from nutrient uptake to improving water quality to really driving the whole aquatic ecosystem in major portions of the river, including for a listed species of fish called the blue-nosed shiner, we, the Friends of the Wekiva River and the management committee overall, needed to have information on the abundance and presence of eelgrass. So, Jim, if you go to the next slide. So first, and really when we were trying to seek a firm to help us with this baseline, really all we wanted was documentation of where the eelgrass was today. And we went through several different people who bid on the project, and Trutta gave us not only that baseline, but several other features. And Jim's going to go into greater detail about that. But we got these detailed maps that sort of confirmed some of what we knew, but provided this visual classification of where eelgrass is and some level measurements of abundance, whether it's highly abundant or common or rare or what have you. And in this map, the areas, the redder it is, the worse it is. In other words, the lighter colors are where the eelgrass is. We understand the areas in red. There are some real reasons why eelgrass isn't spread across the basin, but having this baseline graphic here in this documentation was really the reason we contracted for the work. But Jim, if you go to the next slide. The other thing that we got out of this, and this is going to be really future research additional monitoring, greater work that's going to kind of drive how we manage eelgrass in the system is the Trotter report helped us with predicting where eelgrass should be. And Jim will probably talk about some of the multivariate statistical analyses that define the parameters that were most important for predicting where eelgrass is. And so we have now this database that says where eelgrass is and where it should be. And that allows us to focus on those areas where it should be, but is not occupied for future management. So from our perspective, this gave us a tool that's not only great for baseline, but it's predictive and it's capable of helping us with management over the long term. So we're excited not only about the results that we've got now, but also how it's going to be a useful tool for us going forward.
Good deal. So, thank you for that, Jay. I saw that Jack Frost had his hand raised. Go ahead, Jack.
Yeah, now I'm finally seeing pictures. Sorry about that. I wasn't seeing the slides, so that's why I was going to ask if I needed to do something. So I now do see a slide. So thank you.
Good deal.
And thanks so much, Jay, for that introduction. And I'll give a sort of a brief introduction to the high definition stream survey approach, and then go into the actual Wekiva project. I will say, and with putting the hand up, you can put your hand up. You can also use the chat, and Brett can check those and sort of interject. If you see me looking off to the side when I'm speaking, it's because I have multiple screens and you all show up on the side screen. So without further ado, where this whole thing came from was actually with Paul Ayers on there. It was work he did at University of Tennessee years ago. And then with Brett, looking at the issue of, we have really good ways to look at the sort of bottom microhabitat or site-specific surveys. We've always been able to go out to rivers and count the rocks or measure the depth and look at all different characteristics in 100 meters or in a set of transects. That's been done for a long time. Very intensive sampling at basically a site. And at the top level, in the last, I'd say 50 years, the use of satellite and aerial imagery has exploded, and almost everybody has seen this, where we get super detailed aerial imagery at this point, and it's just phenomenal to use for a lot of management issues. The problem we have is we end up with blue lines that represent streams and rivers. We have a lot of trees that grow on the shores of them, and so you can't really see the stream, or when you do, a lot of times it's a little too turbid to see the bottom. So you end up with just a blue line on your map that has these sampling points that are very hard to relate to something as giant as the whole river basin. So trying to figure out a way to sample at the sort of middle level where we can get 20, 50, 200 miles of survey done at high enough resolution to take those point samples and then tie it into the overall landscape models has been the sort of the goal of the high definition stream survey approach. And on the right side, you see this hypothetical stream with a start and a finish, and we just don't know what's going on in it. And those, the yellow stars could be your sampling sites. And while you know a ton at those sampling sites, we just don't know what's going on. So with HDSS, we can come through and rapidly inventory and assess at about 1 meter spatial resolution. It's really 1 second resolution we put it, so it's about 1 meter. And you can see things like, oh, here's outfalls in your system, but they're okay. They're not really causing a problem. But you can also then see these green outfalls that have weird pollution coming in. You can see where cows are getting in the stream and destroying stuff. And then the red spots of stream bank problems or other things. And it's laid out so that we understand the context, the distribution, and the severity of the issues. So no longer are we guessing what's in the blue line. We know exactly where everything is. And it's a very easy way to monitor change over time. Very similar to the satellite imagery or the aerial imagery where you get a picture from 2 years ago and you compare it to a picture from yesterday and you say, where did it change? This is a very similar approach. You see exactly what was done during the survey, go out and resurvey it at a future time, and it's very easy to sort of do 1 meter to 1 meter comparisons. What data do we collect? Actually, that's interesting. Paul Ayers, who's on this presentation, who's a retired professor from University of Tennessee, is in the back there with Brett in the front. We collect video, both left, right, and forward, so we can see the stream bank, the riparian areas, and infrastructure. We have underwater video looking at, in this project, SAV, and a lot of times substrate. There's sonar running that gives us depth, imagery of the bottom, and allows us to do a lot of bottom classification. Water quality sensors with a suite of different possible things on it, including the typical DO, pH, temperature, and those type of things. We can run acoustic Doppler current profilers when we need discharge specifically. We can collect the bathymetric transects without it, but it's excellent for getting discharge measurements. We do, on many projects, water grab samples because the water then can be sent to a lab for much more detailed analysis than can be collected from a sort of a water quality sonde that we can deploy in the field, and also allows us to do eDNA sampling to, for those who don't know, that's looking at different species, the presence of different species upstream of the site you're sampling. So it's a really interesting way to get sort of a network of where potential animals could be found within the system. But the critical thing is that it's all linked to the GPS, and all of these things have a time, a location, and an elevation. So basically we're seeing each second of the river having a point, and all of this information gets tied together. So it's a very easy way to look at everything. We currently use backpacks, kayaks, inflatable boats, and larger boats. But the reason that I show this is the system that we run and the different features allows us to go from the very top of a watershed. We do a lot of backpack surveys where there's no water, going down through dry creek beds all the way to where there's water. Some of the smaller water, we run kayaks through it. And then as it gets bigger, we have motorized inflatable boats that collect the information, allowing us to have one sampling approach that's not wadeable streams versus non-wadeable streams. So we can collect a continuous set of information throughout the system. We also can collect a whole bunch of more information with tablets while we're going along. Drones can be used in certain situations, and autonomous boats can be run to collect additional information. So the approach works across a wide range of platforms, but gives us sort of a single output, so you don't end up with different results from different platforms. Here's an example of the stream view video coming out of the Wekiva River survey. And again, you can see very clearly on the left, you can see into the water, beautiful here, see the condition of the stream banks and the bottom and the different aquatic plants growing. We have a map of where you are, the down underwater imagery. Over here, there's side scan sonar and down looking sonar running. We also have water quality running that's not showing on this picture.
And one good thing to note, Jim, just to chime in, all this video is recorded with 1080p. It is beautiful video. Sometimes over these virtual meetings, it looks a little choppy. So if it doesn't look perfect, it's purely because of this virtual meeting. And I just wanted to reassure all the video is high definition and 1080p. It looks great. Yeah.
Thanks. It looks great on my side, and I always forget that it does come through depending on how the speed of your internet connection. One of the cool things is that the video is linked to the GIS system. So here, this is actually Brett walking upstream on a tributary to the Chattahoochee River just outside Atlanta. And you can see stormwater damage here in this system, but you can see him walking upstream. There's a parking lot here with a little bridge. And So if I want to know, well, what's the condition of that bridge? You just click on it and then you're downstream of that bridge and we can look at it. We can look at the condition of the stream banks, the stream bed. Here, there's a lot of damage. And then, is this infrastructure in good condition? And so a very easy way to navigate around working in multiple different GIS platforms. And that the important thing for those of you who are not GIS specialists, that's a geographic information system. And that basically means it's a database that has the time and location inside it, allowing us to say this second of video was collected on this date at this time. We know its location, its latitude and longitude. That's actually also embedded in the video. And then we have a whole bunch of different classifications. This was for our stormwater project. And so we're looking at the condition of the banks, and we have this red area. Well, this stream bank is no longer a natural stream bank. It's actually a wall going into a parking lot, and it shows up just beautiful. And we can go through here and look at these conditions. It allows us to cover big areas. Here's a municipality with a stormwater survey done on all their systems. This sort of shows a 5-line approach where the riparian, the stream bank, the stream bed, the right stream bank and right riparian are all labeled at once, and the red would be bad and the green would be good. So you can see where we have parking lots, there's not much riparian development. The stream banks and these things are continuous variables. You always have a stream bank or a stream bed regardless of whether it's good or bad. But we also collect discrete points. So these things don't necessarily occur everywhere. That would be things like pipes flowing into the river, bridges, down trees, cattle getting in there, trash piles. All of these different things are also mapped, and it can be all combined up into what the managers are looking for. In this case, they were looking for areas that they could do work on to improve the condition of their stream. So this is a red to green, where the green areas, if you did work, it wouldn't really change anything. They're already decent. And red areas are areas if they could absolutely improve. And so it gives them that spatial context, very similar to what you're going to see in this presentation for aquatic vegetation. But in this case, this is for stormwater restoration. We collect water quality parameters going along. You can see the boat coming down Falling Water River here in Tennessee. And then you see a big switch right here. Well, there was an out of compliance water treatment facility up here that was just continually failing. And you can see the change. It's a specific conductivity, but it's an approach where you can see where the impact happens and you can calculate how far downstream this impact occurs. So this is a change in specific conductivity. You might wonder what those red dots are. That's us dragging the boat out of the water over log jams and back into the water again. So we get air signatures in the middle of it. And then the bottom imagery is very helpful also. And this is a side scan sonar path going down a river. You can see coarse boulders and ripples in the fine sand. So we're able to classify the bottom from bank to bank. The black area is where the beam hits the bank, and so it can't see outside of it. We can measure and do all that kind of stuff on it. And we can ground truth it with underwater video. So we can go and say, oh, was our boulders exactly what we expected? And so it allows us to do that. But it's also a really excellent way to look at change over time. The whole approach deals with change over time, but having good imagery of the bottom of the rivers is very useful. This is on the Coosa Bypass in Alabama, and there's a large hydroelectric dam upstream of this, and they were releasing environmental flows to hopefully enhance endangered mussel habitat. And the mussels would be living in this sort of rocky substrate, not in the mud. And you can see this little notch here, which is the same location 3 years away. And it's very easy to see the change in the amount of coarse sediment as a response of the management actions. So we can easily go through and quantify sediment movement and the distribution and the amount of the different types. So a very effective way to look at that. So that's a general overview. We do lots of different type of projects, but it's that approach is the same thing. As Jay said at the beginning, they were looking for a way to initiate a monitoring program to determine if eelgrass is expanding, contracting, or holding steady. Well, that's a change over time kind of issue. The first thing we need to know is, where is it today? And so in response, we used the HDSS approach to document eelgrass and a number of other river characteristics. This was done May 17th to the 24th, over 56 kilometers or about 35 miles. This section here was impassable. It actually comes down here and circles around. This is a swamp full of trees and no defined channels, and past hurricanes had dropped a lot of trees across it, so very difficult to try to get through. This other section did have a defined channel, and we were able to go down through it. Again, Jay mentioned, and we'd like to thank the National Park Foundation and Fish and Wildlife Foundation of Florida and everyone on the Wild and Scenic River Mapping Subcommittee. This was a really interesting project where we had to do a lot of adjustments to the system to make sure it worked good for the task at hand. And they were super helpful in coming up with ideas to use on this approach. First step was to create a stream view video. And again, I showed a little earlier, this is just going to loop around through here, but you can absolutely see the eelgrass and then the lack of eelgrass and other, in this case, algae that's growing. Here's the side scan sonar. I'll run that one more time, and you can see the high density of eelgrass up here, and then it changes, gives you the map and the sonar imagery. So a very nice way to look at it. This was completed for the whole system, so this is now available for the whole Wekiva section. How did we determine where eelgrass was? This had to be designed with help from the committee, in which submerged aquatic vegetation doesn't grow under these dense stands of emergent vegetation. And so it's basically in the open water sections of the channel. So we need to know the channel, and we need to know how much of it has emergent vegetation, how much is open water. Then within the open water, we had a classification basically running from 1 not observed to 5, completely covering the bottom. And sort of a very simple classification, but allows us to rapidly go through and determine this. And so what we end up with is basically a combination of the amount of emergent aquatic vegetation and eelgrass and open water. So in some cases, there's very little of anything, and in other cases, it's very dense all the way across the whole river, the amount of vegetation, and then we have to determine whether it's emergent or submergent. And here's an example of that. We can see eelgrass here on the right and no eelgrass on the left. You can absolutely see the emergent vegetation. And in the side scan sonar, it looks like the shoreline is very close to the boat right here, and that's because the eelgrass bed is blocking it, yet it's clear to this side. We can see some eelgrass in the, or submerged aquatic in the down sonar. So we not only did a visual survey looking at the eelgrass as we went down, we did a sonar survey of submerged aquatic vegetation. I'm using those words specifically. Visually, we could tell eelgrass from other submerged aquatics. With sonar, we can't tell species, so we can only say that it was submerged aquatic vegetation. But we used that to sort of QA/QC the approach. Here's what it looks like. We saw this at the beginning. Here's the eelgrass visual classification, green being very abundant and red being not present. Here's the emergent vegetation on the right side. And you can see there's a high correlation between the two of those right now, but the emergent vegetation is more common than the submerged or the eelgrass. So from a very first question, in 4 days, we were able to determine that over 4 kilometers had extensive eelgrass beds, basically covered every bit of the bottom in the open water areas. And over 14 kilometers, or about 30% of this river had eelgrass as common or more abundant. So immediately we can answer that question of where and how much is there. And that's good to see. 30% of this river has eelgrass in it, where in other places, in some of these spring runs, it's almost completely collapsed. And for comparison, here's the sonar classification of SAV, and you can see they look almost identical, except there's a little bit more. Again, we weren't able to determine to species level with sonar, so any submerged aquatic vegetation was being classified as present. But the two approaches were extremely close to each other to support that this is an effective approach to determining eelgrass and submerged aquatics. And then as a graphic for that, here's the eelgrass survey. Over here is the sonar survey. You can see it's basically the same distribution with a little bit more, as I said, and the emergent vegetation is more common throughout the system. That'll become important here in a second. From an inventory perspective, we did a lot of habitat characteristics, first being water depth from sort of a whitish color to red being deeper. And the beauty of GIS is you can come through here. In this case we're separating out Blackwater Creek from Rock Springs Run and the Wekiva River proper, and you can see the distribution of depths. The takeaway message is the majority of this system is less than 2.5 meters deep. So that's the interesting thing about it. This is a shallow water spring-fed system. We have exposed channel width. This is basically looking at the width exposed from tree line to tree line, and it changes drastically from extremely narrow in some sections to very, very wide in other sections. And this is very important to the abundance of aquatic plants. Habitat type, we're able to define sort of the classic riffle run pool, but in this case, shoals, shallow runs, and pools throughout the system. Again, they're defined. We can specify the size and amount of every one of them. Again, the GIS is great because now we can go through by segments and determine the different segments and their distribution. And there are some segments, some of these shorter runs that don't even have pools in them at all. They're so shallow. So it's kind of a neat way of looking at your system. Bottom hardness is a product from sonar, which looks at how far the sonar goes into the substrate. Softer substrates absorb more of the sound wave than hard substrate, and we're able to classify that. Then we have right and left stream bank function modification and right and left riparian function. So there's actually 4 lines here. I'm going to zoom in a little bit. On the riparian side down here, this is some of the few development that's occurring up to the water edge in this area, in this wild and scenic area, and you can see it has an impact. Interestingly, down here, you can see a little bit of color that's on the stream bank. And these are areas where boat traffic is causing bank erosion. So a lot of power boats are coming up from the St. Johns River, running up into here to see this gorgeous system, and the wave action from them is affecting the stream banks. So that's also defined in the system. And then we have water quality parameters, a whole bunch of them: temperature, DO, specific conductivity, turbidity, pH, CDOM, nitrate, and ammonia. I'm just showing CDOM, which is basically the color of the water. These are major spring runs happening here. As Jason at the beginning, there's many springs in the system. This is basically a swamp, and highly forested swamp with what you'd call black water coming through it. So this is sort of that tea-colored water. So this section is a lot darker than this section down here. We also put bathymetric cross sections throughout. These are for channel capacity measurements. And then an additional thing that was done on this project was we wanted to QA/QC the visual eelgrass results. Could we actually see across the whole channel and identify eelgrass effectively from our boat platforms? And so we had the underwater cameras running on these transects. We went through and classified exactly what was underneath the boat, compared that to what we got from our longitudinal surveys, and we had super high correlation between those two. So it was an effective way to determine the presence and amount of eelgrass. And then we took that information to look at a suitability model from what was an ordinal logistic regression model. But the important side of that is the environmental inventories basically define habitat availability throughout the system. And then eelgrass presence and density is what we would call habitat use. And so from a classic perspective, where does the plant occur and what are the characteristics of those areas that it occurs? The model basically came out with 4 important variables. All of them are related to the amount of light that hits the bottom. So we have depth. If it's too deep, then there's not enough light reaching the bottom and the plants aren't growing there. The width was important because in narrow areas, the tree canopy was covering the whole river, and so therefore no light was getting in. CDOM, again, is the water color. The clear water sections had more than the dark water sections. And then emerged aquatic vegetation, or emergent aquatic. And this was a curved relationship where when you had a lot of light coming into the system, both submerged and emerged aquatic vegetation were common and increased together. But in areas where the emergent vegetation covered the whole river, then submergent vegetation dropped off. So this sort of relationship was set up. As we saw at the beginning, the relationship was very tight. I think it was just under 80% of the classification was within 1. So if we said 1 had no occurrence of eelgrass and 5 was complete, 80% of the time we were either a 5 was a 4 or a 5 was a 5. So we were predicting very closely where that occurred, and there was only a small amount of complete misclassification where we said it would not occur and it did, or the inverse of that. So you can see that the observed and the predicted do correlate highly, but you can also see that we tend to over predict. So the prediction is suggesting that there should be aquatic or eelgrass in these areas, and we didn't see that. Now, as a conclusion to that, most of this misclassification were in areas where the model was predicting some level of SAV where none was observed, and those are false positives. That could totally be that the model is not that great yet and we need to improve it, and it could be the influence of unmeasured factors. There's natural variability in the system. The eelgrass beds may grow and sort of diminish in a natural cyclical fashion. We have boat traffic, which we noted on the lower end of this, that had prop scarring and bank disturbances and things like that. That may be limiting the presence of eelgrass. There could be things like localized herbicide runoff. You can see there are developments that are encroaching on this river system, and we did not measure that, but they could easily have it flowing in there. And then the committee explained to us the impacts of past hurricanes. Hurricanes can come in and churn up the water, basically turning it to, chocolate brown, and that shades out the aquatic vegetation. And so there's a potential that we're seeing a recovery. We're always in some state of recovery from past hurricanes. So the hurricanes come in, kill off large areas of this, and then the time since the last major hurricane is how healthy your eelgrass beds are. So that's a really interesting thing. None of those were in this model, but they are all potential because any of these could be suppressing it. The cool thing that we have now is a way to look at this and begin to choose areas to monitor and watch over time to see if we can actually see these patterns occurring. And so from an overall perspective, we were able to rapidly determine the distribution and amount of eelgrass within the river, rapidly document the current conditions of the river, and then create a powerful suitability model for eelgrass occurrence. Again, this took about 4 days to do the complete area. We delivered the complete video, which is all linked to all this different GIS data, which is super helpful to use for not only this type of project, but with all the other information that these organizations have. A full report, including a map atlas of all the GIS data, showing it in paper form. And then we include training with all of these projects because this is a lot of information. It is a huge amount of information, and it is not a sort of a typical thing that you would get, geo-enabled video that works with all kinds of GIS data. So we provide training on how to use all the data at the end of the project. So that occurs on then and makes for a really interesting project. And before I close up here, the goal for the high definition stream surveys is to provide a single way to get your cross-sectional and longitudinal surveys to apply to many different type of projects. We do these stream corridor assessments. You saw some of it on this project. It's very common for stormwater MS4 type projects where you need to know the condition of your stream. We do a lot of work on infrastructure, the location, the condition of bridges, intakes, outfalls, bank stabilization, dams, dam removals. We do a lot of work with hydropower where we're looking at water quantity and quality for, you know, flood risk, drought risk, TMDLs, non-point and point source pollution. Extensive amount with wildlife and fisheries. And you saw a lot of the habitat type work in this one where we're doing riffle run pool, substrate, cover, riparian condition, and tying that to the presence or absence. In this case, that was with Tennessee Wildlife Resources, and they were doing trout surveys that we were modeling. But one of the really powerful things about the approach is the ability to reach the public and stakeholders. So the outreach is really important. Not only do you get this great video where you can go and look at the conditions in the water and see why they're classified certain ways, you have these very simple red-green maps that show where the good and the bad areas of your river want to protect and where do you want to restore. All of these come from a single survey, and they all flow in PA integrated planning framework. So very efficient way to capture the data and take the visual and other sensor information and quickly get it into answering management questions. So this isn't just a let's get pictures of your system, which is very powerful. It has a huge amount of software and classification set up behind it to translate this into the management question of concern and get the answer so that we can begin to get things fixed. And with that, we're happy to take any questions. And Brett's referenced here. You can obviously reach me too, but we do this kind of work. I think we're over 2,000 miles of rivers across the country at this point, collecting a lot of information for a lot of different reasons. So with that, I'd be happy to take any questions.
Hey, Jim, go ahead and go back one slide to that integrated planning framework. What's funny, like when we first started back in grad school with Dr. Paul Ayers, who's actually on this webinar right now, we were only concerned with looking left and right, documenting bank erosion hazard index. And that was like its primary goal. That got peer reviewed, published, and since then it just keeps on growing and growing. And one thing I noticed that's not on here that we need to get is we do acid mine drainage prioritization, working with a whole lot of mining reclamation. And then we're also getting involved with disaster recovery. And that disaster recovery, that was our most recent project up in, I just realized my camera was off. Our most recent project was actually up in the New River of Virginia, and we knocked out 170 miles of river, and we had 2 people on the water and 1 driver. We were able to knock out 170 continuous miles in 12 days of river survey. And again, just going back to that primary slide, being able to connect the dots between those traditional point assessments and then the, you know, big landscape type modeling that you can do. And so again, it just keeps getting better and better, and every single project we do, it keeps getting better and better.
Absolutely.
So it looks like some additional people joined throughout the presentation. Let's see.
Morgan, you have your hand up?
Yeah. So, I'm thinking about that from the pedostinum perspective, some of this work. So, pedostinum is usually in pretty fast flowing and somewhat shallow, like riffle run kind of habitat. So, do you think something like this could be possible for, a smaller aquatic vegetation species like that?
Yeah, 100%. And the kayaks, we go through a lot of riffles and rapids and things like that. Even the rafts are good for the more rapid sections. But yes, it would work great for that. If I had video from a whole bunch of different places, we could probably look directly at it because it's easy to see that. It's easy to see the water willow. And so, yes, it would work very effectively for it. And then it ties to all of the other variables that you may be looking at.
Yeah, it'd be interesting because, a lot of, I think pedostinum is so tied to geomorphology in terms of where it can actually establish. So it could potentially be useful to put some more thought into it.
I'm going to answer a second spin off of that question. I don't know how to go through that this exactly correctly, Brett, but that's okay. I'm going to go to this. We're talking about plants. We were talking about submerged aquatics and emerged aquatics. And then, Morgan, you asked about other species. Well, another big issue with this is invasive species, because a lot of times, and I would assume Florida deals with this extensively, you get water hyacinth and a bunch of other things in there that can have all kinds of impacts on the native species. This is the upper Delaware River on the border of Pennsylvania and New York. And when Brett and I did the survey up here, we're cruising down the river looking at and going, well, there's this beautiful bush with these gorgeous flowers. It's a gorgeous survey, a blue ribbon trout river, beautiful area to go through. And we're going through this survey. And the reason for our surveys was trout habitat suitability. So we're building these habitat suitability models for the trout system. But after the survey happened, we heard that they were having a problem with an invasive species called Japanese knotweed. And one of the strengths of this approach is we're not going out with a fixed, we have to do this. This is Japanese knotweed. It was easy to see. All that had to happen after the surveys were completed. In the past, if I didn't record it on my survey, it was lost. The only way to do this was to go out and redo 80 miles of survey. Now we could go through, actually, this is probably video, but there's the Japanese knotweed on both banks, and you can see where it doesn't exist and where it does exist. Brett was able to go back through this and then just watch the video and define it for invasive species. Green is absent, red is where the invasives occur, and you can zoom in and see every meter of the river, but we can get it down to the exact meters this invasive species is in, and you can look at the percentage, and basically they're looking at 45% of all stream banks covered by this invasive. So the idea of not only are your natives tied to the geomorphology, they can also be tied to whether or not invasive species have gotten in your area. And so we can see both of these things. We can see all of these impacts going on at once. This is an example of doing other species, but also an example of we didn't even know this when we did the survey. It's not why it was done. We were able to get that super easily out of this product without doing an additional survey, with just doing a very limited amount of work. So it's very effective when you don't actually know what's controlling the system. And this species has impacts on trout habitat also, but that's an aside onto a different whole topic. I think, yeah.
And so one question that came in is, does our survey have the ability to be used to update firm mapping? And that stands for the flood insurance rate map with FEMA. And Jim will probably be able to speak more on this. It has not yet. We've worked with some like map boundary changes or like river boundary changes. We have not done that personally, but our data has been used. Go ahead, Jim.
Sure. So for a couple things, I don't have it loaded up right now. We have run this in conjunction with LiDAR surveys and to get 3D channel dimensions. So we're getting complete bank dimension, bank height, and then the riverbed dimensions. So we can do that type of stuff. That would have to be then tied in with an aerial LiDAR or some type of aerial survey so that you could see the extent of the flood zone at different stages. So it does not answer all the questions, but it absolutely does answer a lot of it. With this project, I think I can go back to, which we just did 160 miles going from North Carolina down here to West Virginia, all through Southwest Virginia, looking at the impacts of Hurricane Helene. One of the out products was not to do flood mapping, but was to determine the impact areas. And we were using multiple different aerial and satellite imagery tied into with what we were doing to determine which areas were most highly impacted and develop a model to predict that for this whole river system. And at the same time, document a whole bunch of other information like everything that got swept into the river and as they need to recover from this, all of that kind of identification is being done. But the whole system got documented, all of the scoured banks and all the different issues that were happening. And then that was used to create a predictive model on flood damage. So not exactly the flood map, but going into the models to predict the damage associated with that flood map.
And I believe that was Brett Parsons from Augusta, Georgia asked that question. How did that answer your question, Brett?
Yeah. So I just recently moved to another county municipality, and so floodplain administrator is one of my roles, and I'm going through all the firms, and it's like, oh, they just kind of showed the banks of each river or stream or whatever as the floodplain boundary, and there's nothing else actually included. And so just trying to get a feel for what it's going to take to make adjustments to that, because I feel like it's very base level and we're at risk because of that.
Yeah, and I guess I could say a couple more things to it. In these pictures, you can see the bank height, and then you can see the access to the floodplain. And some of these, there's almost no access to a floodplain. It goes straight up, and other places there could be quite a bit of access. And so one of the things that we can see in a continuous variable is where are the low spots. within that system. So not just the banks, but where are the banks prone to flooding? And then looking at the channel dimensions, you can look at predict velocity over different stages and look at the direction. So we can see where the river or the water power is going to be greatest and where it could likely do the most damage. So it is definitely not a simple where are the banks approach, but the flood map, as I know them, does need to have that stage sort of put out to where that water would flood the area. That isn't sort of this plus typically would be done with aerial LiDAR. Put those together and you'd have your answer beautifully done.
Thanks.
The next question, Tara Harder, she's with the Southwest Florida Water Management District, asking about what types of cameras do we use for geotagging and incorporating into GIS. And she also states that the district does biennial seagrass mapping and is always looking for other options for capturing field verification videos of seagrass communities.
Well, excellent. I mean, we can absolutely talk on different ways to approach that. A lot of this is done, we've used a lot of different cameras. So first of all, there's always testing going on. I'm the head of research and development for the firm. So that's exactly what I do a lot of times. And if my desk spun over here, you're going to be looking at all kinds of cameras and computer parts sitting all over everything. But we're using GoPros a lot. The camera, we also can use networked cameras. The georeferencing side of this work is not so much the camera, it's the approach to make sure that as we capture the GPS or the GNSS, but the GPS data, we know the exact time and we have a link to every sensor that's fixed so that we don't end up with any sort of offset or mistake in timing. So there's a lot of work that goes on to make sure the timing of the sensors is all correct. The sensors, including the cameras and water quality and sonars and everything, are always correct with the timing coming off the GPS. So the sensor, the platform is rather sensor agnostic. You could change cameras, you can change water quality sondes, we can change sonars. That's not the issue. The issue is, can we make sure that they are always perfectly timed? And if they are, all the data will integrate very easily. So the big question is whether you have a camera that is consistent and works consistently over time. And you would think that would be a simple issue, but it's not once you get to these day-long surveys.
Thank you. We use a lot of GoPros as well, and we had an underwater drone for a while that you could watch live stream as well with GPS. But the GoPros is what we've been using, and then obviously with the GPS and boat tracks and things like that. But really neat work that you guys are doing. I appreciate you sharing this with the community.
Yeah, thank you.
Thanks for joining and thanks for the question. And I believe Madison Trowbridge is one of your co-workers, and I've met her at several conferences and also met with her in FDEP. So I'm pretty optimistic of more future work happening in Florida. So hopefully we get to pop down in the Tampa area here in the near future.
Yeah, thanks, Brett. She's actually the one that passed me your way, so I appreciate you guys working with her. She's in our section.
Perfect. I love it. Let's see. I wanted to call out. So Jack Frost, where we were talking earlier, you're up in Alaska dealing with navigability. And I understand, I mean, this project right here was focused on eelgrass and submerged aquatic vegetation and whatnot. But I mean, do you see the value of it for the river management issues you're having up in Alaska?
Well, there's a lot of great data I've seen based on this. One question I do have is, what are your limitations in remote locations where, there may not be access to networks or, anything like that? It's, mountainous, fly-in only, there's a lot of obstacles.
The So now to elaborate on that, back when I was in grad school with Dr. Ayers, we had to pull over every 45 to 50 minutes to change the lithium ion batteries and to put in a new, 16 gigabyte micro SD card. All of our cameras now are externally powered, and lithium ion batteries are getting better and better. We have you can have terabyte cards in your GoPros. Now, I believe terabyte, or might be 512 right now. I forget what each camera that comes out, there's a new, it's a bigger micro SD card that you can have in there. But we've, like on the New River, I turned on all the equipment. We went for 9 hours and 15 minutes straight on nonstop. I had a gallon of water and a bag of beef jerky. So we turned on the equipment and we go. And so, just let the equipment do the work. That's the beautiful part of it. The technology's there. And so if you're in a remote area, it'd be a matter of like micro SD cards are small and inexpensive as far as I'm concerned. And so if you need to have 100 of them on your boat, you can do that. And then energy would probably be the next issue. And so that's, whether we have multiple batteries, and I guess like thinking about Alaska, you could have solar panels if you're working during the summer. And even if you need to, have a supply boat with a diesel generator to charge those batteries overnight while you're resting and downloading data. There's, heck, Starlink capabilities. Like there's ways around it. It won't be as easy as doing the Chattahoochee River in Atlanta, where I literally, Jim and I didn't even set up a shuttle. We just used an Uber whenever we got done with the survey, and I had a taxi ride up to go get my truck at the top of the watershed. So every project's a little bit different, but in your regards, it'd just be a little bit more planning ahead for whatever type of work you're planning on doing. And Jim, if you got anything to add to that, I feel like
I'll also add that I also said we were somewhat sensor agnostic. We have tried to be platform agnostic because we basically have a hub computer inside a Pelican box along with all the other sensors, and it has connections on the outside, so we could mount them on all kinds of different boats or rafts or whatever you guys would be flying in. So it's not as if it has to be mounted on a specific system. We could easily be flying in rafts that I'm sure you guys use already, and then setting up the system on it, hooks up to the frame. You'd hook the cameras on, you'd hook a few other sonar and things on, and away you'd go. So, the battery power is an issue. And like Brett said, you could use solar or generator, but it also the platform, it is really quite basically designed for what is the system you're running? What is the best platform for you to use? And I just from watching Outdoor Channel kind of stuff, I've seen some places in Alaska you can run them with outboards or jet boats and things like that. And if you have that, you have an alternator and you could use that to charge. I'm not sure where you're talking about. So it depends, right? Yeah. But it is relatively platform agnostic. That's how we can go from backpacks to boats to autonomous boats, and it's relatively sensor agnostic. So we could set the sensors to answer the questions that are required there.
Okay. Thank you. That's awesome.
I'll switch pictures while we look for something else. Oh, I'm going to just talk. Do you have a question, Brett, coming up? Or if not, I'm going to show you.
One did come in from Brett. Georgia Southern did an abroad program to Nepal that did remote sensing in the middle of a preserve in the Himalayas. Storage and energy was the only limitation, and that was in 2007. So yeah. And now we got Starlink now too, that keeps getting better and better. And so if we need to, at the end of the workday, beam up data files and or video, depending on how good a connection we have, there's plenty of options.
100%.
You're going to touch on habitat suitability?
I was just going to touch on this. We talked about habitat suitability in this thing, and we talked about the seagrass one, but it could be hellbenders, sturgeon, recreational species and everything. But suitability as a general thing, whether it's suitability of where do you fix, suitability for species. It's a very important topic, and it's so well supported. This is a IFIM type study, so an in-stream flow incremental method, which is a very commonly used approach for fisheries. And we were able to replicate their stuff across the whole upper Delaware, looking at here's adult brown trout and where it's good and where it's bad. And we have it for spawning habitat, juveniles, all these different things. That's pretty straight translation to what we heard with SAV. But we have suitability for recreational use. And on the Chattahoochee River, this is basically Atlanta going to be over here. This is super, super high use area. Chattahoochee's a beautiful river. And one of the questions was, where could they direct people to go wading or fly fishing? And so you can come down through here, set up a suitability model looking at depth, roughness, and velocity, and identify all the areas and how difficult it would be. Similarly, we're able to do that with boating. And so areas that's very easy, well, all the way to difficult. And they have school kids who want to come out and go out in a canoe or a kayak, to people who want to run these whitewater sections. And it allows the whole thing to be defined, same data set, whether we're looking at species, whether we're looking at recreational use, whether we're looking at about anything, whether we're looking at recovery issues like we were talking about. So the suitability can be for project restoration, it can be for human use, it can be for animal use or plant use. It really doesn't make any difference. The beauty is we can collect so many different variables in a single pass that it makes all these models possible to generate from one output. So if we weren't talking about your all specific issue in terms of submerged aquatics, it's we're using it on many, many different types of issues right now.
Yep, and Jack was asking about the recording, and so yeah, like whenever this webinar wraps up, I'll be sending a follow-up email to everybody, because we had about 32 people register and not everybody was able to make it. So I'm going to make sure that we send an email to everybody there, but then we'll also have it in next month's newsletter, which most of you should be on that list. And then also, if you follow us on, LinkedIn or Facebook, we usually are pretty good about sharing our YouTube channel videos up on that. So yes, there will be a recording of this available to anybody, and we'd be more than happy to have you forwarded on.
Thank you. Thank you.
Yep. Thanks for joining, and I appreciate the question. And yeah.
Any other questions?
If kind of the next steps, if anybody has any project ideas, it doesn't even need to be like you have to have funding available for something right now, but if you just have projects in mind and like want to get a rough order of magnitude to make sure we're in the same ballpark, we're putting together rough order of magnitudes a little bit quicker now, but don't hesitate to reach out. My email, I'll put the email in the chat right now, and I'm sure you guys can figure it out via Gmail, but just reach out anytime. If you have any project ideas you want to discuss, if you have a specific body of water you want to discuss, just don't hesitate to reach out. We field those questions all the time and are getting faster and faster with the response. And so obviously zero obligation, just don't hesitate to talk to us. Appreciate it, Ashley. Good deal.
All right. Well, thank you so much for listening to the presentation. Thanks for all the great questions. Thanks, Jay, for your introduction to the project. This whole submerged aquatic vegetation mapping was really interesting and is extending onto other locations now with everything we learned from this project. So super interesting. And thank you all for your time.
Thank you. Bye-bye.
Yep. Y'all have a great day. Thank you.
You too. Thank you. Bye-bye.
All right. Well, goodbye, everybody, and hopefully we'll talk to you soon.
Good deal.